Hi, my name is Talia. I'm a staff member at Discovery, and I'm going to help you do your homework today.
So in this question, you're flipping a coin. And you do it 24 times, and you know that in those 24 times, you got heads 50% of the time, plus or minus 18%. And you want to know, if you did the same experiment 1,944 times, what's the same, you have the same likelihood of getting 50%, plus or minus what standard error? And standard error is the key here. That's what this question is all about. So they're just asking you, if you get 50% of your results with 18% standard error, how will that standard error change the more trials you do? And just kind of by reasoning through it intuitively, that this number will probably be smaller because the more trials you get, the more accurate it is to actually 50%. So this question can seem a little bit daunting, but really when you boil it down, it's just some simple algebra. And I'll show you how that works out, because it's not super easy to think about. So first of all, let's take a look at the formula for standard error. So we know that our standard error percent is the standard deviation divided by the square root of the population number times 100. So you have this equation, this is how it's laid out. And we have two standard errors that we're dealing with. This one, this 18% that's known, and this one, it's written as a heart because we don't know it. It's unknown. And kind of solve for this unknown one, let's look at all the information we have about each number and try to figure out a way to solve for this based on the information we're given here. So let's call this first one as E0. That's going to be equal to 18%. And that's equal to, going back to the formula, standard deviation, which we don't know, over the square root of the sample size, which is 24, times 100. And the second one, let's call it SE1. We don't know what it is, so SE1 equals heart equals standard deviation, which we still don't know, divided by the n. We do have the n here. We're told it's 1,944 times 100. Okay. So there's two unknowns here, the standard error and the standard deviation, but there's only one unknown here. And this is just some simple algebra, kind of like a system of equations. If you can solve for the standard deviation here, we can plug it back in, because like I said, the standard deviation between these two different experiments is going to be the same, because it's like the same actual experiment, you're doing the same thing. So if we can solve for the standard deviation here, we can plug it back in and then just evaluate this expression and find the missing standard error. So let's do that on a calculator. So let's start solving for the standard deviation. So just to some basic algebra, divide by 100 and multiply by the square root of 24. Let's do that on a calculator. So 18 divided by 100 times square root of 24. Our standard deviation equals 0.8818, blah, 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 blah. It's super long. Okay. So now that we have this, don't get too excited if you don't have the answer yet. This is a value we need though. We can plug it in over here and just evaluate this expression. So we'll do 0.8818 divided by the square root of 1944, our new sample size, times 100. Because, kind of just thinking about it intuitively, what does this actually mean? This means that for the same experiment, for the same standard deviation, if we increase the number of people, how is that going to change our error? So let's just do that. Again, in a calculator, because I'm not doing this by hand. 1944 times 100, and we get 2%. So that's your new standard error. So replace this with a 2. And that makes sense because we're doing this a lot more times. So we're a lot more likely to get a real percentage of 50%, because you know that a coin toss is going to be 50% heads, 50% tails. So that's why our standard deviation, our standard error goes down so much here.